The signal lasted 11 seconds. 11 seconds of data that rewrote everything astronomers thought they understood about the star system sitting closest to our own sun. 11 seconds and then silence, as though whatever sent it decided it had already said too much. The James Webb Space Telescope had been staring at Alpha Centauri for 72 uninterrupted hours. 72 hours of golden mirror time, some of the most expensive observation hours in the history of human science, pointed at a star system so close that by galactic standards, it is practically in the same room as us. Scientists expected noise. They expected glare. They expected the frustrating blankness that had defined Alpha Centauri for more than a century of searching. They did not expect 11 seconds of structured infrared emission from a region of space that, by every model they had ever built, should have contained absolutely nothing. What Webb detected in that window, and what the data revealed when researchers spent 8 months dissecting those 11 seconds frame by frame, forces a question that astronomers are now genuinely unsure how to answer. Not just whether there's something orbiting Alpha Centauri, but whether the way we search for worlds beyond our own is fundamentally irreparably broken. To understand why 11 seconds changed everything, you first need to understand why Alpha Centauri's silence had lasted this long. Alpha Centauri is not one star, it is three. Alpha Centauri A and B orbit each other in a gravitational waltz that takes roughly 80 years to complete. Two suns circling each other at a distance not terribly different from the distance between our Sun and Uranus. Further out, at a vast and lonely remove, sits Proxima Centauri, a dim red dwarf, the actual nearest star to Earth, separated from its two siblings by a gap so enormous that it takes Proxima somewhere around 500,000 years to complete a single orbit around them. In 1995, astronomers cracked the code for finding planets around other stars. They discovered that a planet's gravity pulls on its host star in a way that creates a faint, rhythmic wobble in the star's motion, measurable if you have the right instruments and the patience to watch long enough. Over the next 3 decades, using that method and others, scientists cataloged more than 5,000 worlds scattered across the galaxy. Alpha Centauri gave them nothing. The problem is geometry. When you have two bright stars in close mutual orbit, their gravitational influence on each other dwarfs the signal any planet could produce. It is like trying to hear a single voice whispering from the middle of a crowded stadium. The noise floor is simply too high. Alpha Centauri A and B had been shouting at each other for billions of years, and every telescope we pointed at them could hear nothing else. So scientists looked at Proxima instead. In 2016, they found it, Proxima b, a planet orbiting within the habitable zone of the red dwarf. A world that could, in theory, hold liquid water. The announcement made headlines across the planet. For a brief electric moment, our nearest stellar neighbor seemed to be hiding an Earth-sized world in exactly the right place. Then came the asterisks. Proxima is not a gentle star. It erupts with flares of radiation powerful enough to strip a planet's atmosphere in a geological blink. Proxima B's year lasts 11 days. It orbits so close to its host that it is almost certainly locked with one face permanently baked and one face in permanent frozen darkness. The habitable zone in this case might be a technicality rather than a promise. Alpha Centauri A and B remained the real prize. Sun-like stars, stable, ancient enough to have allowed complex chemistry to develop, and completely, stubbornly silent. James Webb was not designed to search for planets the way its predecessors were. It does not look for wobbles. It does not look for the dimming of starlight as a planet crosses in front of its sun. Webb was built to see infrared light, heat signatures invisible to the human eye, with a sensitivity so extreme that it can detect the atmospheric chemistry of a world orbiting another star entirely. But Webb has a limitation that previous telescopes did not. It cannot simply point at Alpha Centauri A and see what orbits it. The star is too bright, too close, too overwhelming. The glare fills the detector. Looking for the planet next to Alpha Centauri A with the James Webb Space Telescope is, as one researcher described it, like trying to see a firefly hovering beside the searchlight while standing 3 feet away. The solution required a technique that Webb was not originally designed to perform. Engineers developed a custom corridor, a precisely engineered mask that blocks the light from the star itself, the way you might hold your hand up to block the sun to see something in its glow. It had never been attempted at this resolution, at this distance, on a target this bright. The team ran simulations for 2 years before they felt confident enough to request observation time. They pointed Webb at Alpha Centauri A. The coronagraph engaged. The star's blinding light collapsed to a controlled dark circle at the center of the image, and in the infrared residue surrounding that darkness, at a position roughly equivalent to where Venus orbits our own sun, something flickered. 11 seconds. A pulse of thermal emission, consistent, structured, and, critically, not moving in the way instrumental artifacts move. This was not a ghost in the machine. This was not scattered light playing tricks on a detector. The signal's position relative to the star was coherent. It behaved the way an object in orbit should behave. The team went quiet for 3 days after the first analysis. They ran every test they could think of. They checked for contamination from Alpha Centauri b, whose orbit had briefly brought it into a less than ideal angular position relative to the observation window. They modeled the coronagraph's known diffraction patterns and subtracted them. They looked for the signal in every other dataset Webb had collected that year. The signal held up somewhere in the warm, Venus-adjacent region of Alpha Centauri A's influence. There appeared to be an object with enough thermal mass to radiate detectable infrared heat, an object in the one location around our nearest sun-like neighbor where liquid water and the chemistry it enables could theoretically exist. Follow-up observations were scheduled immediately. Webb was redirected to Alpha Centauri A 6 weeks later. The coronagraph engaged again. The star's light was suppressed. Researchers leaned toward their monitors in facilities across 3 continents. There was nothing there. Not a reduction in signal. Not a dimmer version of what they had seen. Absolute null. The position where the emission had appeared was empty in 11 subsequent observation windows spanning 4 months. Whatever had produced that 11-second pulse had either moved beyond Webb's detection range, changed its thermal signature entirely, or, and this is the possibility that keeps researchers awake, was never a planet at all. 3 competing explanations currently exist. The first is instrumental. The 11 seconds may represent a failure mode in the coronagraph that the team has not yet fully characterized. New technology at the edge of its design envelope does unexpected things. This is the least interesting explanation and statistically the least likely. There is a wide loss. Our fact hypothesis requires a very specific combination of factors that engineers have been unable to reproduce in controlled testing. The second explanation is geological. Some researchers have proposed that the signal could represent a massive dust or debris cloud, the remnant of a collision between 2 large bodies in the Alpha Centauri A system. 2 worlds colliding would generate an enormous burst of thermal radiation. A debris cloud disperses. 11 seconds of signal followed by 4 months of silence is consistent with the edge of such a cloud passing through Webb's field of view and then thinning beyond detection. If that second explanation is correct, it would mean that planet formation around Alpha Centauri A is not complete, that the system is still in a violent churning phase where worlds are being built and destroyed simultaneously, which would mean that what Webb detected might not be a planet that exists now. It might be a planet that is in the process of becoming one. The third explanation is the one nobody in the scientific community is willing to say out loud in a published paper, but that several researchers have now mentioned in private conversation. The signal moved between the first observation and the follow-up windows. The object, if it is an object, had migrated out of position in a way that is inconsistent with any stable orbital path around Alpha Centauri A. The motion, if the inference is correct, is too fast, too irregular, and too directional to fit any planetary model currently in use. What moves through a star system at that speed, in that pattern, is not a planet. It is not a cloud, It is not anything in the existing catalog of known astronomical objects. The paper containing these findings has now been submitted, revised, and is currently under peer review. The researchers are not claiming a discovery. They are claiming an anomaly, a very specific, very structured, very persistent anomaly in the one corner of the universe we have been watching the longest and understand the least. Alpha Centauri is 4 light years away. The light reaching Webb right now left that star system 4 years ago. Whatever caused that 11-second pulse, if it is still there, if it was ever there, is doing something right now that we will not be able to observe until the next generation of telescopes is built, launched, and trained on that same patch of sky. We sent our finest instrument to the doorstep of our nearest neighbor, and not something answered. And then it was gone. The question that keeps the Alpha Centauri research team returning to their data month after month is not whether the signal was real. Most of them believe it was. The question is whether the universe just showed us exactly what we have been searching for, or showed us something we are not yet equipped to understand, because in 11 seconds the nearest star to our sun stopped being a familiar light in the night sky. It became the most important unanswered question in modern astronomy, and the answer, whatever it is already 4 years old and getting further away with every second that passes.